Okay, if we have this fishing floater, this fishing bobber, we basically can use a similar situation to evaluate the stability of ships, and I will show you why. So this is exactly the same situation where we have an external force that can be wind, that can be waves or whatever. And as soon as the external force is gone, you will see that the 3 points crossing in the meta center height. And what is going to happen is, because the B is upwards and the G is downwards, this creates a moment between the two forces. And this moment is what we call the stabilizing moment. And as you can see over here, it depends on the rolling angle phi, and of course of the height of this meta center. And what is going to happen is being shown over here. And the ship will return to a position where it is in equilibrium, where all the external forces and moments are in equilibrium. So the ship is in a stable situation. Now, how can we calculate this? We go to the point K. We have this point G, which is the well, it's a fixed point in the ship, and it's the overall center. We got the center of buoyancy, and this center of buoyancy is depending on the shape of the underwater vessel. So you can imagine that now you consider this shape over here, which is completely different as when the vessel is in a stable horizontal position. So this point changes with the heel of the vessel. And then we got this meta center height, which is a measure for the initial stability of the vessel with the rolling angle phi. And this whole system is basically gives you a way to evaluate the stability of the ship. Now, and if we go to the next step, whereby the GM should be calculated, another simplification is that the KB, when you have a box-shaped barge, and it's applicable for relatively small angles, less than 6 degrees, you can say that the point of buoyancy is about half of the draft of the vessel. Now then, all that come together, we also have the kg, which is something that can be calculated from the moment equitation, and you will add all the different weights up to. You will calculate the moment towards the keel per item. You will add up. You divide it by the total weight, and the result is the kg. So the GM can now be calculated, which is great because you have very simple, a very simple formula, which can be used to at least get an idea of the GM. And as said before, the GM is an indication of the initial stability of the barge of the ship. Now, what we see is that the width of the barge and the kg of the total system is has quite an influence on the stability of the barge, and that's nicely shown in this movie.
Floating objects, such as barges, can move freely in water. The amount of movement depends on the stability of the rig. The more stability, the less movement, and the sooner it returns to its starting position. Stability is determined by the width and depth of the barge and by the height of the center of gravity in the crane masts.
Now this short animation is taken from the movie that was made after the accident in Alphen aan de Rijn, where these two cranes came down because of stability. And it clearly shows that AG, the height of the whole system, together with the width and the draft of the vessel, has quite an influence on the stability. The effect of the stability of a ship can be calculated. One of the things, and that's for this presentation important, one of the things that we always should remember is the fact that as soon as we start lifting, either with a fixed crane on the vessel or with a mobile crane on the vessel, the position of the center of gravity of the whole system will abruptly change when you pick up the load. And it is important to understand how this is going to work, because if you have this situation, hang on. You have this situation with the cargo on the quay, you have a stable situation whereby the center of gravity of the load is on this position. As soon as it's being suspended, the center of gravity of the load is moving from this position abruptly into that position. And you can imagine, if you are operating heavy lift vessels, or you do a heavy lift operation with a mobile crane on the barge, as soon as you start lifting and as soon as the load is suspended, then you have to consider the center of gravity of the load in the tip of the crane boom. And you can imagine that the vertical center of gravity is highly affected by this change of center of gravity. Now, this is the best shown over here in this short movie. Now, what we do here is we fill up the ballast tanks with water, just to create some additional stability. The G is down. We will, in some cases, will add a stabilizing pontoon to the side. For instance, Jumbo uses this, whereby you increase the moment of inertia of the waterline area, and you also can use it as a counter ballast. You can fill it up with water. Now, what is then happening is that she's booming out, she's picking up the load, and what is now going to happen, we have a small roll angle, a small angle here. As soon, with the center of gravity of the load being on the quay, as soon as the load is being picked up, you will see that the center of gravity moves from this position quite fast to that position, and the total GM value is getting to a lower level, and might be tricky when the initial stability of the vessel is not enough. Now, this is going to happen. You will move some water ballast from port side to starboard to compensate for the for this heavy object. What you see now is it's being lowered in the hold, and as soon as it's put down in the hold, the center of gravity gets back to the position of the center of gravity of the load. Now, this is one of the issues we want to pay attention to. Again, as soon as we got a load hanging in a crane, being suspended, make sure that the calculation is being made with the center of gravity is placed in the tip of the crane. And that's really important to.
Now for cranes, the next sheet. Classic approach for cranes is we put it on a flexible support. We ask whether the lists of the machine or the heel of your barge, what it's going to be. We ask the naval architect, can you make it, can you keep it upright, and what are the tolerances for it. That tolerance is put in our crane calculations in terms of an additional machine list. As you can see in the summation, the last one. The crane specialist knows about all these evolved techniques in the latest years because of the fact that the cranes are going longer, more slender, and he is aware of this new calculation skills which he needs to make these calculations, in which all flexibilities are taken care of from top to bottom. So that's not completely new, and that's not the point we want to make here in this presentation. So more or less some additional machine list. That is the classic approach for the crane specialist. And in the next sheets, the point we want to make to you is it's not only GM value, it is also mass. In the sheet before, we will skip the part of the transport or the SPMT in which the pendulum is standing instead of hanging. So it's another seminar in which we go more in detail into transports. However, here in this situation, we want to give you a first indicator for stability. As we have seen in the sheets from Tom, the GM value itself says very much about stability. When it's negative, you have a negative stiffness. So it's unstable, fundamentally unstable. When it's very high, then it's very, very stable. However, how should we interpret a GM value? And that's an issue which passes many times. We have seen this 3% rule from IMO. We have seen this 10% for heavy lift vessels. 10% of the width of your vessel or barge. However, it's not a very 100% rule, because when you are on a very small barge with low masses and high mass ratios, and with high mass ratios I mean that the mass of the barge is low related to the mass of the load, the SWL. For example, at Alphen and the Rhine, it's about 10% the load versus the vessel. The vessel was 1,000 tons, the load was 140 tons, so that ratio is quite high. And when these ratios are high, then these 3 or 10% rule are not 100%. So the point we want to make is that a low GM value is not always a problem. So how to interpret, and the market and the standards don't give real good, how do you say, a good answer on that. And we gave this as maybe a better interpretation of stability. What we do is we see the complete system as two pendulums. The first one is the pendulum of the complete system. So the mass in the tip of the crane and the mass of the barge at the end. And then you have a shifted GM value, as you can see at the right picture, a shifted G. The blue line, the dotted blue line, the small dotted blue line is the GM value when the SWL is in the tip of the crane. So the complete red line from top to bottom is has an overall GM value, GM, and a pendulum stiffness as a result. However, at the tip of the crane, there is also a moment. So not only the masses in the tip of the crane, when you have an off lead, you also have a moment. And that moment is made by also a pendulum. And that pendulum has also a stiffness. So the moment acting on the tip of your crane is a result of the length of this pendulum and the angle of this pendulum. and the mass, which is hanging there, the SYL. As you can see at the left, you can then, as a result, make two calculations of two pendulums with two stiffnesses. The barge, ending with 387 kilonewton meters per degree, and the pendulum of the load, it has a 634 kilonewton meters per degree. So to put it into perspective, 634, no, take the barge stiffness, it's 387 kilonewton meters per degree, is let's say 38 tons on a meter delivers you 1 degree of trim. That is exactly what it says. 38 tons, 1 meter from the center line of your barge delivers you 1 degree of rotation. That is exactly what a stiffness says. So these two stiffnesses, when you relate them to each other, you get a kind of amplification factor. In this case, calculated for the Alphen accident, and it delivers you a 1.6. This means, and then we go to the right, you see these two angles. What happens when you shift the load with a 1 degree off lead? What happens with your heel of your barge? There is a factor of 1.64 in between, and that factor is saying a lot more than only the GM value, because when that factor is, let's say, below 0, then you have a very confident feeling, and when this factor is in terms of what you see here, then you don't have a very confident feeling. So in the next month or the coming time, Eager One is intending to search a little bit more about giving a kind of maximum amplification factor. At this moment, I have the idea to say when it's below 1, then it's kind of safe, and when it's below higher than 1, then it's not safe. However, we are coming up with next theory on this subject. What you see here is quite new. I haven't seen it before. This interpretation of these two stiffnesses, relate them to each other, and then give a more better indication, which is very simple to calculate, not much more difficult than the GM value itself. So should give more interpretation to this stability. It's a first indicator for stability. The second one, and then we come up with the next sheet.
Welcome to this illustrating movie in which we want to explain more about the stability of cranes on barges. What you see here is a simple pendulum. Actually, you see two pendulums. You see the crane length and you see the pendulum length representing the GM value of the barge. This is the meta-center. This is the CUG position of the barge. So this is the GM value of the barge, assuming that the wooden part, so the crane and this part, doesn't have any mass. Now you have a simple representation of only a barge with the CUG position here. First, we want to make a point here, and that's the point that stiffness of a floating situation is not only the GM value, it's also the mass of the complete system. So the complete mass displacement in terms of volume multiplied by 1 ton per cubic meter, and then you have the complete water displacement, and that complete mass represents the mass of the complete system, and that represents a variable also important determining the stiffness. So it's not only GM value, it's also mass. And these two values multiplied by each other, so mass multiplied by the GM value, the pendulum length, give you the stiffness. To illustrate that, this is a stiffer situation than this situation. Only because of the mass is higher. GM value is for both situations the same. Metacenter, COG. So the pendulum length is the same for both situations. However, mass is higher in this situation, so stiffness is higher. So point we want to make is it's not only stiffness determined by GM value, it's also mass. Illustrating the second point we want to make is illustrating a crane picking up a load from the deck, which will result in a shifting COG position and a lowering of the GM value, and with a lowered GM value, a lowered stiffness, and in some occasion a negative stiffness, and a negative stiffness will go immediately in an unstable situation. And that's what we want to show right now. We pick up a load from the deck by decreasing the amount of pieces of lead here by 1, and we will hang it in the crane hook here by this simple situation. Okay, we put it in the hook and we take off one of these from the barge deck, and now we have the following situation. It's secured now by my fingers. I will desecure it and you will see what happens. There it goes. In this situation, it is very unstable. By adding this mass, so making the complete mass of the system higher, we will see that it's less unstable and even stable. However, the amplitudes are high, so it's not a safe situation. That's a different one, because a positive GM value will not say you it's a safe situation. The stiffness will determine whether it's a safe situation. That's another thing which we have shown in the pictures in the presentation, that the amplitude of your off lead relative to the amplitude to the rotation of the complete system, this ratio will give you a figure about the real safety in case the GM value is positive. But it's very hard to illustrate that with this prototype, so this one we only want to illustrate the effect of picking up a load. It's the end of the movie, and I hope that this will give a lot of clarification to the stiffness of cranes on barges.
Just an example. The example which we have shown in the slide before was a 6 Sennebogen on a barge. Don't remember the barge, however, is not important for this situation. It was for a specific customer. And here you can see that we have made the red one is the original land-based Sennebogen rating. We do this in most situations in close cooperation with the manufacturer of the crane itself. So Sennebogen mostly is aware of our changes in ratings. And here you see an example of the fact that we have made 2 situations for different kind of side leads. It's all what the customer wishes. He wants to operate with 5 degrees side lead or off lead. Then you get special ratings for these operational circumstances. As you can see, the strength of the boom, it's the horizontal piece of the brown line, makes you delivers you a shortening in your capacity from around 110 to a little more than 60. So that's quite something. But this is just an example to give you an idea about this way of operating our calculations.